All right, lecture 16. Let's pick it up. Just a note, at the end of last class, I was looking at the numbers and I realized half the class is actually over. Okay, the midway point is lecture 14, right? 7 classes. And so we are actually in the second half of this course in terms of time. All right, let's see. Supporting in. Wish there was an easier way to switch in Zoom. Okay, there we go. So then the last topic I wanted to cover was active filters. Active filters basically work the same as the passive filters that we studied in 201. They utilize the energy transfer concept, the energy transfer phase of the capacitors and inductors, and use it for filtering functions based on the frequency of the incoming input signal. Again, a quick and brief recap. Capacitors and inductors are energy storage devices. They receive the energy from the source, from the circuit, and then they release it back into the circuit at a later point in time. So there is an energy transfer that takes place constantly between the capacitor and the inductor and the circuit. Now, this energy transfer cannot take place instantaneously. It takes a finite amount of time for the energy to be transferred back and forth. This period is known as the transient period. Now, if it's a DC applied voltage or current, then the capacitor or inductor would receive the energy and store it and then return it back to the circuit. However, if it's an AC, meaning the voltage or current, the input voltage or input current is constantly switching its values, positive, negative, meaning they are a function of time. That means energy is constantly being transferred in and out of these devices. And depending on how fast the changes are taking place, the capacitor and the inductor will oppose that change. Remember, reactance is the property of the inductor and the capacitor to oppose any change in the input voltage or input current. And the reactance, basically the impedance of the capacitor, the inductor, and the circuit, basically effectively filters out or blocks out certain frequency signals. Okay, and so we're going to use that property for active filters also. For my classes, students who are not in my 201 classes, I use a concept where we can model capacitors and inductors at low and high frequencies. Capacitor C can be modeled as an open circuit or low frequencies. It can be modeled as a short circuit for high frequencies. And inductors are the opposite. At low frequencies, inductors are replaced with a short circuit, and at high frequencies, they are open circuit. Call this the quick and handy dandy table. Low frequencies, capacitors are open circuit. High frequencies, they are short circuit. Inductors are the opposite. So if we look at this circuit, we have a standard inverting amplifier. Single resistor feedback, single resistor in the input. But there is also a capacitor connected in parallel to that feedback resistor, meaning the output is fed back via the resistor and the capacitor in parallel. So if I wish to analyze this circuit, let's model the circuit at very low frequency. Excuse me. So as the frequency tends towards 0, meaning you're applying low frequency signals, then the capacitor behaves like an open circuit. And the feedback path for this op-amp is simply the resistor itself. Sorry, not the resistor itself. It's just the resistor. Okay, it's just the resistor. So you're applying V in, and then V out is simply And it behaves like a standard inverting amplifier. Capacitor is open. Standard inverting amplifier. So what does it mean? So at low frequencies, it behaves like a standard inverting amplifier. Excuse me. So it is allowing the low frequencies to pass through. Low frequencies are passed. Okay. On the other hand, at high frequencies, as F tends towards infinity, meaning higher frequencies, capacitor behaves like a short circuit. What is happening? Well, quick and easy way to answer this is that V out is connected straight to the inverting terminal. And what happens then? If it's connected straight to the inverting terminal, there's a short circuit between the output and the inverting terminal. Because of the virtual ground or the virtual short, we can say the output is also now virtually connected to ground. So V out goes to 0. Here, V out would be equal to AV times V in. And here, V out is equal to 0. So higher frequencies are blocked effectively. Hence, the circuit works as a low pass filter. Low pass filter. Low pass filter. Make sense? Any questions? Any questions at all? So in the frequency domain, if we are looking at frequencies of the input signal, the circuit is a low pass filter. If the circuit is, if the frequencies are not varying, if you're simply analyzing signals as a function of time, then in the time domain, this is what happens. Same circuit, we are simply interested in a different aspect of the circuit operation. Remember, capacitor current IC is C dVc over dt. Okay, capacitor current I is C dV over dt. Voltage, capacitor voltage Vc is 1 over C integral 0 to t times IC dt. The capacitor is there connected to the output. It factors into the output equation V out. And so V out is integral of V in. And so in the time domain, the circuit functions as an integrator. Okay, circuit functions as an integrator. Any questions? Oh, sorry. So again, different, I mean, same circuit, different applications or different aspect of the same circuit, different model, depends on what we are interested in. If you're interested in the frequency filtering performance of the circuit, then we would analyze the circuit in the frequency domain. If we are interested in using the circuit as an integrator, then we would simply analyze it in the time domain. Okay, the same circuit, just different models of analysis. Now let's look at the next one, which is the high pass filter. And in this case, same principle of analysis, makes it easier. At low frequencies, capacitor behaves like an open circuit. And if it's open circuit, because it is in the input path, capacitor is in the input path, it blocks all inputs. Okay, capacitor blocks the input. At high frequencies, capacitor behaves like a short circuit. And if it behaves like a short circuit, and capacitor passes the input. So low frequencies are blocked, high frequencies are passed. Hence, the circuit works as a high pass filter. Works as a high pass filter. And in the time domain, voltage, sorry, in the time domain, the circuit works as a differentiator. Differentiator, opposite of the integrator. C dV over dt. Okay. Derivative of the V out would be a derivative of the input voltage. Input voltage. Let's take a pause while you write it down. Let me know if you have any questions. The circuits, again, this is not going to test or assess students on these circuits, but this is something that students should be aware of. You know, how we can perform different mathematical operations using an op-amp. Okay, just by adding one single component, we can convert this op-amp, or we can function and use it as a summing amplifier, a difference amplifier, a low pass filter, high pass filter, integrator, differentiator, any kinds of instrumentation, multiple kinds of instrumentation amplifiers. Okay. And then one last circuit I'd like to show is cascaded stages. Cascaded stages of amplification is very real in real life. Most circuits that you would see, whether it's in your smartphones, mobile devices, like smartwatches like this, have instrumentation amplifiers with cascaded stages of op-amps. Here, you see a low pass filter. So let me do this. Let me draw a boundary right there. And let's draw a boundary right here. Okay. This is the low pass filter. This is the high pass filter. And this is simply an inverting amplifier. Okay, inverting amplifier. And these are known as cascaded stages. Cascaded stages meaning simply the output of one circuit is connected as input to the next one. And so they are cascaded. Output, input, output, input. And when you combine low pass filter and high pass in the same circuit, you obviously get a band pass or a band reject filter, depending on the frequency, the cutoff frequency. Okay, depending on the cutoff frequency. So what is happening here is these are unity gain active filters. Okay, there is no gain being applied in the first two stages. Okay, there is no gain being applied in the first two stages. Any gain we want is obtained in the last. So here, oh, what happened? What did I do? So I would say AV is equal to -1. AV is equal to -1. And here, AV is equal to minus RF or RI. So the last stage or the third stage is simply functioning as a amplifier. That's all it is doing. Okay. All right, so this is the end of chapter 3, which is op amps. From here on out, it is all logic circuits or digital logic circuits. Okay, combinational and sequential logic circuits. And this is the this is going to form the bulk of the remainder of the course. Okay, chapter 4. So chapter 4 is basically logic circuits or digital logic circuits. So far in 201 as well as 321, we've been working with analog signals. Analog signals are basically continuous signals, right? This is an example of an analog signal. It can take any shape. Analog signals can be square, triangular, sine waves. Oh, that's not quite a sine wave. Sine waves, or rectangular pulses. Now, all of those are functions. Digital signals seem similar to square rectangular pulses. So in digital signals, what happens is we still have voltages, we still have currents, but our thinking from the human side, not the machine side, thinking from the human side is that we are going to work in the binary number system, meaning the circuits can only take, not circuits, but the systems can take only two values. Okay, can only take two values. Those values are represented by zeros and ones. And again, that's what we'll be studying in this class. But the example of the digital signal that you see here is that it's a flat line, right? It's either at the negative value or at the positive value. Negative value or zero is basically one value in the system. At the other end is number one, okay, zeros and ones. One of the advantages of analog versus digital is that it has inherently a higher signal to noise ratio. Okay, signals are all around us. When I say signal, we mean wired signals, wireless signals, any kind of quantity that has voltage and current is a signal. It's a function, signal. They're all kind of synonyms when we use, when we use those terms in class. So if there's a signal around us that we don't want to enter into our system, we term that as noise. Okay, noise is present everywhere around us. So if this is a standard signal that we want going into our system, this is that same signal with noise. And that can be A real life example of that can be interference that you obtain in, let's say, your wireless radios. Anytime you try to tune your AM or FM radio station to a particular station, anything that interferes with that same radio transmission is unwanted, and hence its noise. With digital-based transmission, digital has 1 and 0, right? This is 1 and 0. So the system considers a high value as 1 and a low value as 0. So even if there is noise attached to both 1s and 0s, the system still reads it as 1 and 0. Does that make sense? So actual voltage or actual current might vary. The value might go above or below that level, but because the system is designed to consider that high level as 1 and the lower value as 0, it still simply functions. So inherently by design, a digital system has a higher signal to noise ratio. That's one of the biggest advantages. That's why they always say, right? Oh, digital is always better than analog. Digital signal is better for transmission. This is where it comes from. So it doesn't mean that there aren't any drawbacks. Digital systems also have their own drawbacks, but the simplistically, this is the biggest advantage of a digital system over the analog system. So how do we define it in terms of voltages? So in terms of voltages, let's say, now typical value would be from 0 to whatever your supply voltage is. Your supply voltage would be VDD, and this would be 0, right? 0, just negative end of your voltage supply or ground. And VDD could be any value, plus 10, plus 15, let's say plus 20 volts, right? So we define the system, or we design the system to work for a certain range within that high value of VDD. And then we also design it to not work or work at the low end at 0. So if this is your VDD, meaning your max value in terms of voltage, and this is your minimum value in terms of voltage, then we define this region as logic 1 or logic high. And this voltage is VIH, and this one is VOH. Okay. And again, that depends on the design of the system. Does that make sense? Right? So we have logic 1 and we have logic 0. We still have voltages, we still have currents, because the circuits are comprised of the components that we studied, right? Diodes, transistors, PDs. Those are the components that make up our digital circuits. There's no difference. There's voltages, there's current. But the circuit is designed in a way that will only function for certain range of voltages or not function for certain range of voltages. And that's where the digital comes from. So what we use for these are BJTs. We have FETs, field effect transistors. We have MOSFETs. These are not part of the course. And remember in chapter 2, when we talked about transistors, we said normal mode of transistor operation is the active region, where we use the transistor as an amplifier, right? That we consider that as the normal mode of operation. In the digital system, the normal mode would be using the transistor as a switch. And a switch, a mechanical switch, is the best example of a digital system. A mechanical switch, let's say you have a light bulb, LED or filament lamp, doesn't really matter. You have a switch, either it's on or off. It only has 2 states. The voltage when it's off is 0 volts, and the voltage when it's on is 110 volts or 120 volts, right? The voltage level doesn't matter. The state is what matters. The state of the mechanical switch is 0 and 1. If it's 0, the light bulb is off. If it's 1, the light bulb is on. The circuit itself doesn't care what we call it, right? We humans call it as 0 and 1. Engineers, circuit designers would call it at 100 volts, 120 volts. The system itself is not sentient. On and off, that's all we do. If we put a dimmer switch in there, now that dimmer switch has multiple levels. That's again a different discussion. But for the most part, if you have a switch, as we have in this room, you turn the power on, that's digital 1. Turn the power off, it's digital 0. Does that make sense? Let's take a pause, think over that. Let me know if you have any questions. Any questions? So as I was saying, the analogy can be made between analog and digital as a mechanical switch which is off and on. And off, we can say, if we represent the same system, same mechanical switch in the digital domain, we can say off is logic 0 and on is logic high. Okay, 0 and 1. Our circuits are made of BJTs, FETs, and MOSFETs. They're all transistors, different kinds of transistors. The point being that we do not use them in active mode. We use them either in cutoff or in saturation mode. If it's in cutoff, we call it as digital 0. And when it's in saturation, it's conducting. Output is at maximum. We call that as digital 1. We do not allow the transistor to enter into the active region. Okay, that's the big difference. When we use it for analog circuits, we want to operate the transistor in the active region. When we are working, we are using the transistors in for digital circuits, then we use it in cutoff and saturation regions. So here, here in the circuit, so not circuit, sorry, in the diagram that I have here, we have 0. The minimum level is defined as logic 0. You have a defined region where the digital circuit is said to be operating logic 1. And here we say it's operating in logic 0. Now, what happens if you have noise signal coming in? What will the system do then? If you have some noise coming in, then you have to build in some noise margins. There has to be some noise margin built into the system so that it does not inadvertently take a 1 as a 0 and a 0 as 1, which still happens in real life. Which still happens in real life. So we have to build the system with some noise margin in mind, and that's what the NM stands for, noise margin. Okay, remember, not remember, the signal right here where I said noise can affect the signal, meaning it could either increase or decrease the voltage, but the system will still take that to be 0 and 1. Voltage fluctuates, in power lines, right? So if you turn on a light bulb, if the voltage is supposed to be at 110 volts, it might drop to 100 or 90 perhaps, but the filament light bulb might still keep working on. Nothing's going to happen to it. If the voltage increases to 120, 130 volts, it'll still keep working. It's not going to turn on. So in that case, the filament light bulb is designed to work within the noise margin of plus or minus 10 volts. So if the voltage increases or decreases, it still operates and still works, stating that it's within the noise margin. Now, if the voltage, if you flip the switch off, the voltage is supposed to go off all the way to 0. But let's say there was 10, 15, 20 volts going through that circuit. It's the low end. It's supposed to be 0. It's supposed to be off. Perhaps the bulb does not turn on at that low, at those low voltages. That's the low end noise margin. And that's the similar concept that we apply here. The noise margin at the high end and the noise margin at the logic low end, logic low level. Okay. So if this is the point where we want to work, we can define a smaller region for logic 1 and for logic 0. And the rest of it can be devoted to the noise margins. Okay. Now, real life logic circuits typically work either from 0 to 5 volts or 0 to 3.3. Okay. So real life digital circuit voltages range from 0 to 5 volts. 0 volts is low end and 5 volts is high end. So we would define digital logic 1 as the voltage range from 3.5 volts to 5 volts. And logic 0 can be defined as 0 volts to 1.5. Anywhere in between is undefined, meaning the system doesn't know what to do. And so we take care to design circuits that it doesn't go in the undefined region. Okay. So far, so good. So a digital signal looks like this, and we represent it using the binary number system. Binary number system for 2, right? It's got 2 values, high and low, 2 states of operation. Two states of operation. High and low. Okay, it's either on or off. Okay, on or off. Anytime I want to explain the binary number system, I always like to use this meme. How many of you have seen this before? There are 10 kinds of people in the world, those who understand binary and those who don't. Yes, no? It's a binary number system. That's why it's 2 raised to the base. In the decimal system, 0 to 9, we have 10 values. So the multiplier is 10, 10 raised to 0, 10 raised to 1. Binary number system, you only have 2 values, zeros and ones. And so the multiplier is 2. So it's 2 raised to 0, 2 raised to 1, and it will make more sense when I explain the system. This is another joke I like to use. This is actually from Professor Bland. He used it many years ago when he first did 321. And so I borrowed it from his slides. But I particularly like these 2 memes. I'll explain the previous one, but this is just a joke. Kids being kids, trying to outsmart parents. But in the end, it's my way or the highway. Anyway, Binary number system, again, we only have two options, right? So it's based on powers of 2. Decimal number systems, 0 to 9, have 10 numbers. Hexadecimal has 16, 0 to 9, and then A, B, C, D, E, F, 10 plus 6. So the base is 16. So again, there are lots of number systems. Octo number systems have a base of 8. But again, our focus for this class is going to be on the binary number system with base of 2. Okay. When we describe numbers, we have the least significant digit, and we have the most significant digit. Same thing as the decimal number system. The one that is on the right is the least significant, and the one that's on the left is the most significant. Okay. In a circuit, each number, each line, each wire is defined as 1 bit. 1 bit. 8 bits together, meaning 8 digits together, comprise 1 byte. 1 byte. And that 1 byte is what we use when we say KB, MB, GB, right? Kilobytes, megabytes, gigabytes, or terabytes now, right? Terabytes of storage. Those are these bytes. And that byte is comprised of 8 digits, 8 bits. Okay, so 8 digits of information, meaning 8 wires running from one end, or point A to point B. So binary number system, as I was saying, comprises of, actually, you know what? I'll come back to this later. Let me show you this table. Let's look at this first. Decimal system right there. Standard decimal system, we've been studying this since elementary school. We have numbers going from 0 to 9, right? 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So once you reach the end, meaning you reach 9, that's the end of the single digits. So now you increase the number of digits in there, you increase the number of bits. And what do? If we write in 2 decimal places, we can write 0 as 0, 0. 1 can be written as 0, 1. And then 0, 2, and so on and so forth until we reach 0, 9. Make sense? After 9, we again have 0. So we again write 0 to 9 in the least significant digit. So then it begins again, 0, 1, 2, 3, 4, until we reach 9 again. Then the most significant digit changes. Instead of a 0, now we go to the next one, which is 1. So after 9, we get 10, 11, 12, so on and so forth, until we reach 29. Sorry, not 29. What am I doing? I've confused myself. I got to send back. I got to attend elementary school with my son. After we reach 9, comes 0 again, right? And then we go 1, 2, and so on and so forth until we reach 9 again. Here, this 1 changes to 20. So the most significant bit changes to the next digit, goes to 2. And it stays at 2 until we use up all of those digits. And then we go 0 again, then it becomes 30. And 31, and so on and so forth. Does that make sense? Right? I teach my son the numbers. I've been teaching him the numbers for a few years. So you automatically at that age, when we learn the numbers and the alphabets first, we don't think about it. We simply say, okay, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way to 100 and beyond. We don't think how it's actually implemented, but this is the way it's implemented. Does that make sense? Right? Is the same principle is applied to the hexadecimal system also. The hexadecimal system is 16 digits, 0 through 9, and then the letters A, B, C, D, E, F. Okay. We won't get into that now. I just want to explain the binary number system. So binary number system only has 2 digits to play with. Only 2 digits to play with. So again, this is decimal and this is binary. If you use the same concept, it only goes from 0 to 1. If we wish to describe 0, and let's use 4 digits to describe 0. 0 would be 0, 0, 0, 0. Make sense? Right? 0 would be 0, 0, 0. If you wish to describe 1, you would change the least significant digit, meaning the rightmost digit to 1. Everything else still remains 0, 0, 0. So the first 2 states is 0 and then 1. And then we reach the end. We can't do anything more. We have to increase the number of digits if you want to do that. And that is what is shown here. 0 and 1 is done. Now we have to increase and place one more digit on its left side. So then what happens? After 1, we go back to 0, right? And then the most significant digit changes from 0, 0 to 1. Let's wipe this out so that it makes sense afterwards. And don't worry about conversion or anything right now. I'm just using the decimal numbers as a point to illustrate, because that is the system that we are all familiar with. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Does this make sense? We have the first 2 states, the first 2 numbers in a binary system. We start with 0, the second one is 1, and then it's done. If we wish to describe a further numbers, then we have to add digits to its left. And so, thus we get the number 2 is 1, 0. Does everyone see how we obtain 1, 0? Now it makes sense. It's not 10 kinds. That's the well, I wouldn't say trick, but that's where the message is. There are 1, 0 kinds of people in the world, those who understand binary and those who don't. And that's, you see why I like it. I'm a nerd that way. And then if we keep going in the same number system, what comes after 0? 1. So it becomes 1, 1. And then 1, 1, again, we used up all the digits because there's only 2. So now if you want to describe a fourth number, sorry, not a fourth number, a fifth number, then we have to add one more digit to its left. So we add 1 here, and we get 1, 0, 0. And that's how 100 push-ups or 100 sit-ups equal 4. One, 0, 0 is 4. Okay, let's go back to the table. Does that make sense to everyone? Right. And then thus we build up our table. 4 is 1, 0, 0, and then 1, 0, 1, and then the cycle repeats, right? There's only 2 places. So it's 0, 0, 0, 1, and then 1, 0, 1, 1. And so we get, so if you notice, we have these 2 right there. They keep repeating, right? They keep repeating on the right side. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So the least significant bit or the least significant digit can only take two places, right? So it's 0, 1, 0, 1, 0, 1, 0, 1. When you get to the second place, it's 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0. And so then that cycle keeps repeating. So if you take these four together, if you take, so this would be 0 here and be 0 here. If you take these four together, you can see that these four will also keep repeating. It's the same thing for our decimal number system. We just never pay attention to it because it's 10 digits. The same cycle keeps repeating, right? Zero, 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 one, 1, 0, 1, 1. And every time we increase, we add a significant bit, like a most significant bit to it. That can also only take two values, 0 and 1, 0 and 1. And so we get 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. 1, 1, 1 means we have used up the maximum number of 3 digits. We now have to add a fourth one. Okay, we have to add a fourth one. So our decimal system, 0 through 9, that's where is 9. 1, 0, 0, 1. 1, 0, 0, 1. I'm trying to think of the joke that Sheldon made in Big Bang Theory. He brings up a binary. I can't remember what number it was. Do you all watch? Have you all watched the Big Bang Theory? There's an episode he's talking about a palindrome, which is the number spelled backwards and forwards is the same. So he goes 1, 0, 0, 0, 1, 0, 0, 0, 1. And then he says spelled backwards, it's 1, 0, 0, 0, 1 and 0, 0, 1 or something like that. I'll have to dig that up somewhere. But that is the binary number system, right? 1, 0, 0, 1 for 9. And then the rest of them are the maximum that you can suffice for. So this is decimal 6, this is decimal 15 or hexadecimal F. Okay, decimal 15 or hexadecimal F. 4 digits, 1, 1, 1, 1. And typically we simply work with digits that are in the top half. Okay, so 0 to 8, 0 to 9 perhaps, not more than that. So this is a lot of information to take in. Think over this. Let me know if you have any questions. I'm going to end class here today. I'll pick up here again tomorrow, and then not tomorrow, Friday. And then we'll also look at how we can go back and forth between the decimal and the binary systems. Okay. So still have a few minutes. Ask any questions that you want. Otherwise, you're free to leave. Any questions from anyone?
I got a question, but it's not really related to course content per se, if that's okay.
Yeah, that's okay. But so then let me stop the recording first.
Yep.
And then
in case
also
anyone
be
else has
aware
questions,
that
I'll hold
you
on.
are on speakerphone. So if it's something you wish to not disclose at large, then we can talk after everyone is gone.